So now we need to look at an Atwoods machine when it's set up on a slope. It's the exact same process you guys have already been doing, except now we need to look at the vertical and horizontal components of the object on the slope. So as with any problem, before I go into anything, I'm going to label the forces on my objects. We have normal force, which is always perpendicular, and the force of gravity is pointing straight down. In this situation, there is no friction, it's a completely smooth surface. In the next video, we'll talk about how this is different when there is friction, but it really doesn't change that much. You just have one more force to worry about. So we have the force of gravity down, normal force up, and tension pulling up and to an angle. For the 24 kilogram mass, we have the force of gravity down and tension up. Now, since I have two forces of gravity, I'm going to be careful and I'm going to label my objects so I keep them straight. I'm going to make A the object over here and B the object over here. So this would be FGB and this would be force of gravity of object A. Now, just like with before, we can straighten it out. But before we do that, remember that if you have an object on a slope, the force of gravity is not directly along your x and y axis. And this curved axis is still our axis of acceleration. And this vertical axis is perpendicular to that. So we don't have to worry about the normal force or the y component of gravity. We just have to worry about the x component of gravity, since that's going to contribute to the force of friction. If you're not sure about how to do that, you can always look back. But keep in mind, this angle is going to be the same on the inside of here as it is in this triangle. And to find force of gravity of x, it's the force of gravity times the sine of theta, which is going to be equal to 78.7 newtons. And that force horizontally is going to be the same as the horizontal force trying to pull the object down the hill. So Fgx equals 78.7 newtons. Now, just like in the last Atwood's problem, you can always straighten these out and treat it as a system. And when we straighten this guy out, force of gravity of object A is going to be pulling to the left. We have tension to the right. We have a tension pulling to the left. And we have the force of gravity x of object A, the horizontal component of the force of gravity of object A. So now, if we create our net force equation, we're going to do it for the system because that's always a great place to start. And then if you need to, you can always come up with the individual net force equations for objects A and B. We're going to start with the system. Net force of the system is mass of the system times acceleration. And the net force of the system, forces, I'm going to treat clockwise as positive and counterclockwise as negative. Or rather, in our straightened outline, to the right is positive and to the left is negative. FGA is to the left, so it's negative, negative FGA. Tension is to the right, so it's positive. Whoa. This tension is to the left, so it's negative. And FGXA is to the right, so it has to be treated positive. That's equal to the mass of the system times acceleration. Mass of the system would be the mass of object A plus the mass of object B, which is going to give us 36 kilograms times the acceleration. Now, we have FGA, which is equal to 24 times 10, mass times gravity, negative 240 newtons. Plus Ft minus Ft, remember, internal forces are going to subtract out from each other. Plus Fgx of A, which we found was 78.7 newtons. And that's equal to 36 times acceleration. So when we combine negative 240 and 78.7, we get negative 181.3 newtons equals 36 times acceleration. And to solve for acceleration, we divide both sides by 36. And then we find the acceleration is equal to negative 4.48 meters per second squared. Now I want to highlight the fact that we have a negative acceleration. That's really, really, really important whether we get a negative or positive acceleration. Keep in mind we treated this way as positive and this way as negative. So if we get a negative acceleration, that means the object is going to accelerate up the hill. That's going to be extremely crucial in the next problem where we add friction, because the friction will work against the intended motion. All right, so now we need to introduce friction into this situation. And your first thought should be, whichever way it's trying to accelerate, trying to move, friction is going to be working against you. It's going to try to accelerate in this way, which we found because we got a negative acceleration. And remember, we chose this way as positive and this way as negative, or rather to the right is positive and to the left is negative. Now, if it's trying to accelerate in this negative direction and friction is trying to work against it, that means friction is going to be working against it, pushing down the hill. So now we need to figure out what this external force is. Using the equation, force of friction equals the coefficient of friction times the normal force. We know the coefficient of friction in this situation is 0.5, but we don't know the normal force. And that's where that free body diagram where we drew all of our forces before comes in handy. We know it's not going to accelerate up into the sky or down through the slope, so we know our vertical forces on the 12 kilogram mass have to be balanced, which means the normal force has to be perfectly balanced by the y component of the force of gravity. And remember from before that the y component is Fg cosine theta. In this case, it's 90.6 newtons. And if that y component is 90.6 newtons down, then the normal force needs to perfectly balance it and be 90.6 newtons up. And once you have that normal force, you can plug it directly into the force of friction equation, and then you get 0.5 equals, or times 90.6 newtons will be your force of friction. So we're going to find that the force of friction equals 45.3 newtons. Now, this is starting to turn into a mess, but fortunately we have our system equation up here, our system diagram. So I'm going to add that force of friction there. And from there we can get a new net force for the system equation, which is following the exact same steps as before. So I encourage you to pause the video here, see if you can work through it, calculate the acceleration, and then unpause it and see how you did. So let's work through our net force equation for this system. Net force of the system equals mass of the system times acceleration. So we have Fgx and Ff are positive, Fgx plus Ff, and then we have plus Ft and minus Ft, so we can ignore our tensions because they're going to subtract each other out, and subtract the force of gravity of object A. And that's equal to the mass of the system, which again is going to be 12 plus 24, which is going to give us 36 kilograms, times the acceleration. Fgx we already found to be 78.7 newtons, plus the force of friction, which we just found to be 45.3 newtons, minus the force of gravity of A, which is still 240 newtons, and that's equal to 36 kilograms times the acceleration. We can combine these three into 116 newtons. Have to be very careful about your positives and negatives, and that's equal to 36 times the acceleration. Divide both sides by 36, and we're going to get negative 3.2 meters per second squared. Because this is negative 116. Negative 116. And that's your acceleration. Good.